Hello and welcome to this session on milliohm testing, and we're going to look at the importance of resolution and accuracy when you're taking this measurement. Typical scenario is going to be either earth bonding or phase winding. So we have a motor here that does have a fault on there. We're going to look at the balance between each phase, and that's where this tool comes in, our new milliohm meter, MT03A. So this is a USB device, new software, and with a unique feature of being able to measure 3 phases in one measurement using the 4-wire method, the 4-wire Kelvin method, which is completely accurate and allows for any tolerances in the test leads as well. So you're only actually measuring the physical point of contact. So from point of contact to point of contact is where you're measuring resistance value. We also have temperature compensation. So we have a 3.5 mil jack plug that goes in the back of the milliohm meter, and in the case of measuring phase, we'd place this as close as we can to the motor winding because we need to compensate. Remember, the coefficient of copper for measurement is the temperature for that measurement is 20 degrees. Any compensation will be carried out by the software, as you'll see as we move on. Where I really want to go with this is just the limitations of using something like a conventional multimeter for this measurement. Now, this is by no means redundant. This is a perfect tool for continuity and accurate measurements, pretty much from 0 ohm all the way up to mega ohm. But it's when you start to drop below 0 ohm into the milliohm region, this is where we can sometimes have an issue. I guess the best way is to demonstrate this. So we use the Pico meter, and we'll connect as we would normally, and we'll measure the 3 phases on this motor. Remember, we won't be compensating for temperature. What we would do normally is take the temperature value at the time of the measurement, maybe an infrared device, and then calculate accordingly using maths. But if we just go through this measurement here, so we'll go from U to V and note the value on the meter. And we are about 40, 50 milliohm, give or take. So that's U to V. We'll go V to W. Let's make sure we've got a good connection there. Again, 50, 40. And then finally, U to W. And again, 50 milliohm. All right, let's repeat that test using the new milliohm tester from Pico. So you'll notice here that we have 2 leads. Remember, this is going to be a 4-wire measurement. We've got the red marker on the test lead to go into the red 4 mil connection socket on the device. And we'll try and connect, or we will connect exactly as it says there. So we'll have U, V, and W as we've labelled up. So U here is going to be blue. Connection is paramount when you're doing this because any connection error is going to result in an increase in milliohm resistance. Next up is V, and then finally W. Now, I'm going to let those hang because I don't want in any way the weight of the cables pressing down on the crock clip so as to relieve the pressure on the connector. Remember, we've got temperature compensation here as well. Temperature probe is simply dropped into the motor assembly. This has been out of the vehicle for quite some time now. We'll open up the milliohm meter software, and we'll click on electric motor test. Accept the warning, and this pretty much is as straightforward as it gets. If you just notice in the pictogram here that we actually test by passing current through the winding. We start with U and V. We then reverse that current. That allows for any thermal EMF effect from differential metals being connected to connections and via crock clips, etc. And finally, we come to the last phase, W to U, and there we have it, a balance motor. Yeah, 19 milliohm, 18.8 and 19 milliohm. And the bar graph there, that pretty much tells us that those phases are balanced. Now, depending on specification, that is either a good or bad. I believe that is okay for that motor. The balance is what's important there, but just grasp for a second how low that resistance is. 18 milliohm, 19 milliohm. It's a tiny, tiny resistance. On that subject, if ever you do get an erroneous measurement, repeat the test. So, sorry, before you repeat the test, take your clips off, reapply them and repeat the test. Just see what happens. If you then get a good result, that was obviously a connection error. If it's the same phase with the same error, then that is most probably a true erroneous reading, and then of course we have to diagnose further with the motor. So notice there, we did, I guess you could argue, have balance with this, but this read approximately 50 milliohm per phase. The actual true reading using this 4-wire method was 19, 18, 19, give or take. So far more accurate using the milliohm meter with far better resolution. Okay, so another neat feature with the milliohm meter is the fact that we can log resistance, and we can actually plot resistance over time. So I've taken away the green because we're just now going to use U and V phase, or the blue and yellow test lead, because we're going to switch modes in here now. Go to the home screen and we'll go to milliohm meter. And what I want to show you here is just how resistance changes, either with connections or with width of the cable, or even the length of the cable. As we know, the longer the cable, the wider the cable, the resistance changes, and just what influence connections has on resistance. So coming back to this test here, let's just measure test lead resistance. So we'll choose the red test lead and we'll add a crocodile clip, and we'll clamp onto there using the Kelvin clip, and at this end we'll clamp onto the probe tip of this test lead, and it's 21.7 milliohm in that lead alone. Let's repeat that with the black test lead. Same procedure again. Let's make sure we get good grip there. There we are. 22. So remember, during that first measurement of the phase, we actually had a resistance of 50 milliohm approximately, of which the majority of that would appear to be test lead. So trying to measure that phase conclusively with this style meter is challenging. Okay, on that subject, let's just have a look at cable resistance. So here's one of the Pico test leads, breakout leads that we use in our lead set. I'm just going to join them together. So we've now got a loop of cable there. In the end, I've got a brass 4mm male adapter, just so as we've got a good point on which to clamp. So we'll go from that point there and we'll go to this point. So we've now got that style connection and a resistance of 4.2 milliohm. Notice in the graph there that if I open, we go open circuit. Of course, if we clamp back down again, yeah, so we're graphing in real time. So let's say 4 milliohm, and we'll repeat that loop again with black test lead. So clip on here. Same point again. Now we are 13 there. That's interesting because that connection there doesn't feel as tight as the other one, as in the spade terminal. So I'm going to give it benefit of the doubt. Okay, so we got 30. Let me just change my position there. No, I think we've got it, yeah, 11 milliohm. Okay. What we'll do now is we'll join these two together. So we'll just lengthen these leads. And theoretically, we should have the value of both added together. Clipper here. And here. Okay. 12 milliohm. Watch what happens when I open the loop. So we're still connected, but there we've jumped up now to 18, 19 milliohm. Okay? So there, just simply by opening that loop, if you like, we've still got continuity through the other half of the loop, but the resistance increases. So why are we sort of so concerned with milliohm? Well, think about the current that would pass through certainly high voltage cables. If you think about 100 amps passing through, let's say 80 milliohm, okay, 100 amp through 80 milliohm. So that's 0.08 ohm, okay. The actual volt drop across there will be 8 volts, so amps times resistance. So 300 volts, let's say battery voltage, high voltage system, but then 8 volt drop across one connection. You imagine the heat generated over time. So milliohm values are, and the accuracy of measuring milliohm values is so important with high voltage, high current systems. Okay, so coming back to this motor, we do have a problem. The balance of the phases were good. What I'd like you to look at now is the resistance to ground. So what we're going to do is between phase V and to ground, we'll go to ground on the motor here. We have a measurement value there of 63 ohm. We'll then go between phase V and ground, that's 77 ohm. And between W and ground, 77 ohm again. So there's something quite interesting there, is that on V and W we had same resistance value, but on U to ground we had something different again. So much less resistance between phase U to ground than V and W. So how could that be of diagnostic value? What we're saying here is, if we refer to the chart here, that the resistance between U and ground is less than between V and ground and W and ground. So if we were to just draw that, how we think what we could have, or where that fault could be, or what we could be looking at here. If U to ground was the least resistance, we could be looking at something like, exaggerated, but let's go with this here. Our short to ground in this motor could be there, because the resistance here, was it 63 milliohm, something like that? But from here to that point, was it about 77, something like that? And again here. So based on that, that would certainly incorporate more resistance, as would this here, because you're traveling through this coil. So theoretically, it looks like we could be looking at something between U to ground, or certainly a less resistance, least path of resistance to ground from U to the ground point. All right, so based on this theory, we know that there's a short to ground. We've proven that with the milliohm meter. Let's have a look at insulation, because that will really confirm what we actually know. We'll use the Pico milliohm meter. We'll use the ground lead, because this will free up one hand, because we can clamp this to the body of the motor. So the insulation meter, of course, we bung this one here now, and we go our positive for our insulation test and our ground, and we'll attach this to the motor casing. We are looking for a short to ground through the phase windings. So gloves on here. We are going to now test at 500 volts. So that's the nominal voltage next level above. So for this vehicle, the test voltage would be 500 volts. And we'll go between, first of all, the U phase. So press down hard here, press the test button. Okay, and basically we've got continuity there. And our test voltage is 7 volts. That's the top right-hand corner of the meter. That's a fail. Move on to the next one. This is now V phase. Again, 0. What it's saying is pretty much continuity between the V phase and ground. And finally the W phase. Press and hold. Yeah, again, 0 continuity as good as, and 7 volts. What we should have seen that is a mega ohm value and a test voltage at 500 volts or exceeding 500. So, based on all that information, we're going to strip this motor down and have a look inside and see if this theory holds up. Will we find something? I'm not sure. It'll be an interesting exercise. What I will try and do is have the milliohm meter attached and logging this resistance value, so U phase to ground, continually. As we take components off, it may be that while I move something, take a component off, even drain if there's fluid inside there, we may actually see that resistance change. So that will give us a pointer. So it's nice to be logging resistance while we dismantle. Okay, just to recap before we actually dismantle this motor, we're set up to measure the phase resistance U to ground. So you see there we are 64 milliohm on U to ground. There's our ground clip, there's our U clip. Just to quickly run through again as a quick refresher, what had we got on the V phase? 77, and same again, we were 77 on the W phase as well. All right, so we'll leave that logging whilst we take components off. Remember, we are temperature compensated, so the results in the top there are the current measurements and the results underneath are temperature compensated. So yeah, at 14 degrees, we'll be actually adding a resistance value because we know as temperature increases with positive temperature coefficient that the resistance of the copper will increase too. All right, let's get going. All right, so we'll just take this drain plug out. I want to see if there's any fluid in there. If there is, of course, we'll get the drain bucket underneath it, but let's just, no. And we're still at 64, so let's see if I can, no. So fluid-wise, nothing inside there that's giving us this issue from what we can see. All right, so now we'll start dismantling. So I've just relocated the earth because we start by taking the end plate off here. I'm not sure whether it will come apart, but let's just see. There's a little bit of jumping around in the log in there, but that may well be to do with connection here. Ultimately, it could be something to do with this end plate. Okay, so that's all bolts removed. Still at 64 milliohm. We'll just give that a tap and see if that changes our resistance. That's a good sound. Ah, now then, that is interesting. We've gone up to 76, which ironically, 77 was the other values. And nothing is changing. This is still gripped here. Gone back down to 64. This is still a good connection here. It does have an effect, or it appears to anyway. Okay. Okay, so we'll break away there. We'll try a few pry bars, see if we can get that movement. I'm not sure whether that's held with something else or maybe even magnetism. Yeah, so we'll come back and lever that off. Try prising in here. Does seem to be giving. And our milliohm value is changing. Reasonably confident that is going to come off now. Something is grabbing it centrally, but it does appear to be giving, which is good. Interesting how our resistance is changing. There we go. That was quite welcome. Wow, what a small motor. Looks as though that bearing has given out. I think that's conclusive. But in terms of our resistance now, where are we? Still at 60 milliohm. Let's have a bit of a tidy up in here. It does look as though this has got hot, looking at the discoloration on the inner race of the bearing. There is also, oh, that's very interesting. There looks to be debris. I don't know whether we can bring the camera in here, or maybe if I turn this over, we see we're at 60 milliohms still. And this is what I'm concerned about, is this here. So that fragments of metal, not sure where that is from. Most likely the bearing, maybe the carrier. Yeah, there's discoloration around here. I'm wondering if I can just fetch, hopefully the camera can pick up on that. Yeah. There looks to be some debris wedged between the winding here and the casing. Yet we're clear all the way around here. So if I fetch that out, I wonder whether we can actually, well, there you are. We have a huge resistance change there. We're up to 12,000 milliohm, 1.2 ohm. So that was definitely an area of a short circuit. And that's changing. All right, so this debris, oh, look at this. That there, which I'm trying to fetch out, look at that. Yeah, that looks like a, sorry, that looks like a ball carrier for the bearing. So it looks to me now as though the bearing has given out. Obviously there's been some eccentric rotation. This breakup has ended up between the windings and the casing. Here's another piece coming out now. Hopefully, yeah, can you see that? That's okay. All right, so there we are. In fact, now we are open circuit, which is exactly what we're after. So an open circuit there means we no longer now have a short between the winding and the casing. With that said, there's obviously damage to the laminate around the coil, which unfortunately deems this non-serviceable. It'd be interesting to have a look at the insulation test now we've fetched that debris out, so we'll repeat the insulation test now. Okay, so we've now got our insulation meter back on, measuring reference to the ground here. We'll go on to the U phase, press the test button. Okay, our test voltage, no, we still have a short through there. Okay, so I was hoping that had moved it. Maybe that there's still some debris left in there. Let's go to the V phase. No, still a short to ground. Finally, the W phase. Okay, so still work to be done, unfortunately, but I think at this stage we know exactly what's wrong and how this winding certainly was shorty to ground.
Okay, so I've just cleared a bit more debris from around the motor winding here, and this is quite interesting. We're doing insulation tests between you and ground, and just note what happens here. You can see the sparks there. Yep. So, out had about a short to ground on that one. We can just go down to V phase. V phase now. Just say, there you are. It's jumping across V phase. And now, W does smell as well. W phase. There we are. Hope you can see that. So, certainly have arcing going on there, where that debris was wedged between the windings and the casing.